Hello, everyone. Welcome back to another week. So today we're going to take a look at section 11.4 and 11.5, the last two sections of chapter 11. So in 11.4, we're going to take a look at spanning tree. All right, so here are a few homework problems you can try on if you want. All right, so take a look at the definition of a spanning tree. So a spanning tree is of a symbol graph is a tree that is a subgraph that contains every vertex of G. Okay, very important. So a spanning tree is a subgraph of the original graph that is a tree and then contain every vertex of G. So a tree is very important because a tree doesn't have a circuit. Okay, so that's why we call a tree. And then it's have to contain every single vertex of the original graph. Okay, so it's a subgraph but defined as a tree. So here is the example that we have. Okay, so yeah, you can try to see if we can pick an arbitrary vertex and can you create a tree out of that, right? So let's see if we can have that concept. For example, we can pick like A and then see, okay, I'm gonna create all the length that's possible. You can go there, you can go there, you can go there. As long as we don't create any simple circuits, then we should be good. So I'm gonna go down here and then I'll go back to this guy. Is there any circuits? No, we don't have any circuits, so we're good. So there we go. That is one option of a tree. So we cover all the vertices that we have. Oh, we skip that one, so they all connected. Yeah, so we can go there to there. Okay, looking good. All right. So here is one option that we can have. Right. So we have A here. So we're gonna go from A to B, and then B to C, and then C to E, and then E to F, and then E to G. Okay, so A start with that. We have B here, we have C there, and we still have D out here. Don't worry, it's not alone by itself. We're gonna connect that in a little bit. And we also have A go to D. Okay, we're gonna have A go to D. So there you go. Every single vertex are connected and we don't have any circuits involved. And you can always go from one vertex to another vertex. So that's a tree. So this is a spanning tree, right? This is a spanning tree. Yeah, you can pick another vertex and then you can do the whole thing. So if I erase my original option and then I can go with a different direction, I can still do it too. So I can pick a vertex F and then I can say, okay, I'm gonna go to this guy, and this guy, and go back here, and then I go back to this one. As long as we don't create any loop, then we should be good. So now I go through all the vertices already, and we don't have any loops. So that's another example. So again, you still have A, B, C, D, E, F, and then G. So now we start with F, and then we go to E, and then we go back to B, then we go to C, and then we go to D, and then we go all the way to G, and then G to A. So again, all the vertices are connected and we don't create any circuits, and that's how we define a tree. And that's another example of spanning tree. Okay, So there's not just one option for spanning tree that we can have. All right. Sounds good. All right. So now we're gonna take a look at how do we find spanning tree. We have kind of two options we have. So the first one is called a technique to do it, depth first search. All right. So any symbol graph is connected if and only if it have a spanning tree. So you can see in the previous example, yeah, we were able to connect all our vertices. Then there's no circuits, then it's a spanning tree. So that's the theorem that we can apply. So if you have a spanning tree, then the graph is connected. If the graph is connected, then we have a spanning tree. Okay, so one or the others. So here's the first option, depth first search. So depth first search is an option where you can generate a spanning tree by pick some arbitrary vertex as the root. So on the exam, I will give you a designated root and you can start from that root so that everybody will have the same starting point instead of, multiple different starting points. So that would be harder for me to grade. So I would pick one as a designated root and you can start from there. But if they doesn't say anything, then you can pick any arbitrary vertex to become your root, all right? So the idea of depth first search is that, okay, pick an arbitrary vertex to be your root, and then you're gonna find the neighbor of that and the neighbor of the other neighbors until you cannot go further, right? So that's what they call depth first search. You're gonna go all the way to create a chain reaction as long as possible, okay? So that's the idea. So we're gonna go as long as possible for that. Right, so we keep adding vertices and edges, and where each new edge is incident with the last vertex in the path and the vertex not already in the path. We keep continue adding the vertex as long as possible. That's what we call depth first search, right? You go for the longest. And then once you go through all the longest possible, and then you can always track back to see which vertex has not been added yet. And then you can do a track back and then add the vertex that we just missed, okay? And once all the vertices are connected, we have a spanning tree. So that's what we call depth first search, all right? Okay, so if it's n, then it's n. If not, we can always move back and search, right? So that's the idea of depth first search. So here's the examples. All right, so again, we can pick any vertex and we try to create the longest chain possible. Let's say we pick vertex A. All right, so we're gonna, again, try not to create any circuits. I'm gonna go A, you can go for A to C, or you can go A to B and then A to C, right? So you can go A to B and then B to C and C to D, D to E, E to F, F to G, G to H, and H to I. So that's the N, you can see it right there, yes? So that's one possible path you can have. Or you can go from, A to C and then C to D, D to E, E to F, F to G, G to H, and H to I. But that is not as long as what you have before, right? So you try to create the longest as possible in the first trial that you have. Does that make sense? Okay. So again, we're gonna go back to the other one. So we're gonna go from here, A to B, and then B to C, C to D, D to E, E to F, F to G, G to H, and H to I. So what are we doing after that? So now we say, oh, is there anything I can do? Or is there any vertex that I did not include? Well, you can see that the vertex J kind of alone by itself. So once you have got that done, and now we're gonna do backtracking, right? So we're gonna go from I, backtrack to H, and then you're gonna go back to H here, and then H to G, and then there you go. And that's when you cover every single thing. Okay, so there's one possible, right? So here's one possible. A will be your root, right? So A go to B, B go to C, C go to D, D go to E, E go to F, F go to G, G go to H, and H go to I. So So A, B, C, D, E, F, G, H, and then I. Okay. And then when we do a backtracking, we know that J connected to G. So that's when we add another section here. So that would be J. Okay, so that's one possible where we start at vertex A. So that's what we call depth first search. So another one here, you can see, you can go from A to C, and then A to B, yeah, you can go there. You get A to B, and then B to D, B to C, and then C to D, and then C to D to F, and then F to E, and then E to H, and then H to G, and then G to J. Okay, that's another possibility that you can have. All right, you can go from A to B, and then to C, and then to D, and then to E, and then to F. Oh, D to F first. D to F, and then F to E, E to H, H to J, and J to G to J. That's still the longest. And then you can go back to that extension right here. Yes. So that extension is H to I. There you go. That's another possibility that you can have. Okay, so that's what we call depth first search. Depth first search. And it's also depend on what vertex that you pick. In this case, we pick A to be the root. You can pick any other vertex. So let's say if we pick, let's say if we pick which one? If we pick E, for example, right? If we pick E, for example. So you can have E go to D, D go to C, C go to A, and then A go to B. So you have 1, 2, 3, 4. You can have 4 layers. And then the other one, you can go E go to F, F go to G, G go to H, H go to I. You have 1, 2, 3, 4 layers. So it's the same. Which one you want to start with, right? It doesn't make any different on that. You can have that for sure. Or you can go the longest if that's possible. You can go E to H, H to G, G to F, F to D, D to C, C to A, and then A to B. So that's also work, and then you do backtracking on that. That also should work, right? You can go there. E go to H, and then H go to G, and G go to F, F go to D, and then D go to C, and then C go to B, A, and then A go to B. And then you do backtracking, right? Backtracking, the only thing that we need to cover is the I and the J. So that's should came out of H and G. So you can do with G. G will have one of those branch, so will be J here, and then H will have one of the branch, which is I. So it's really depend on which designated root as the vertex. Which vertex do we put as the designated root? All right, that's the idea of depth first search. But we try to create the longest chain possible. Okay, so that's the idea. So again, everything have to be exactly the same as the original graph, right? So I and H, they are together, J and G and J, they together, things like that. Okay. So here's the algorithms, right? So first we lay out all the vertices, and we pick one vertex to be the root. So we visit that vertex. So for each vertex adjacent to V and not yet in T, we add that to the H. So now we visit W, right? So and then they keep going on and go on until forever. Okay. So another one is called breadth first search. So BFS. The other one is DFS. So depth first search versus breadth first search. What's the difference? So for the depth first search, we're gonna start one vertex. We go all the way until we cannot go anymore. Breadth first search is different on the other hand. So breadth first search, you don't go all the way, but you go one level at a time. Okay, you're gonna go one level at a time. So you're gonna go level 1, level 2, level 3. So you're gonna go all the neighbor of the first item, and then all the neighbor of the second item, and then all the neighbor of the third item, and so on. That's the difference between breadth first search and then depth first search. Okay. Okay. So we go by layer, right? So level 1 will be all the edges incident with the original vertex. We call that level 1. And then level 2 will be all the edges incident with the vertices in level 1. And then keep going until we finish all the layers. Okay. So I can show you comparison between depth first search and breadth first search. Right. So here's the same example. Right. I'm gonna pick the same vertex A. So you can see. So first I'm gonna have is DFS. So remember what we did before. We get A to B, and then to C, and then to D, and then to E, and then to F, and then to G, and then to H, and then to I. And we're backtracking. We have J is the neighbor of G, so we have J here. All right, so that's depth first search. Now we're gonna compare that with breadth first search. Also the vertex A. But you can see here I have two neighbors, so B and C. So those will be the neighbor of A. There you go. Okay, make sure they're on the same level. So that's B and that's C. So that's level 1. And then C have a neighbor which is D. So there's no other neighbor of C. So we have here, which is D. That's level 2. And then D have E and F. So D will have E and F. So that's the next layer. All right, so F will be, E will have H. And then F will have G. And then H will have I. And then G will have J. So one level at a time. All right, so you can see here, there's different color here, so you can all see it. All right, so that's level 1, that's level 2, that's level 3, that's level 4, and that's level 5. Okay, so L1, L2, L3, L4, and L5. Okay, so that's the difference between depth first search and breadth first search. So breadth first search, you want to go one vertex at a time. Okay, you're gonna go in that order. You're gonna go one vertex at a time. Okay, and you just show you before. It say it will pick E. All right, so E will be the first vertex. So the neighbor of E will be D, F, and H in that order. Okay, D, F, and H. So D will be C, okay, and then C will connect to A and B. There you go. And then F will connect to G, and then G will connect to J, and then H just connect to I. So that is we start from E. Yes, one layer at a time. Now that's the difference between depth first search and breadth first search. So breadth first search, you look at one layer at a time. So one neighbor at a time, one vertex at a time. That's the idea. Make sense? Okay, here you go. So here's the algorithm again, right? Just exactly how I explained this to you, okay? So moving on to 11.5. So 11.5 focus on, yeah, it's a spanning tree, which we focus on in section 11.4. But now we're gonna look at, but is that a minimum spanning tree? So this kind of reminds us to describe algorithm, find the shortest path from one vertex to another vertex. But again, the shortest path only focus on a graph, meaning that it could have, you know, a circus. But when you talk about a tree, then you only focus on the graph without any circus. So now we try to find, can I find the smallest tree possible? And that's what section 11.5 is about. So here are a few homework problems you can try out, okay? All right, so here is the definition. So minimum spanning tree is a connected weight graph in a spanning tree that has smallest possible sum of weight of its edges. So similar to this kind of algorithm, right? This one we look at the weight again. So here's the example, okay? So you can see that I can create a bunch of spanning tree if I can have that. So I can have here, there, and there. That's the spanning tree, yes. That's the spanning tree. Or I can have, you know, 1, 2, 3, 4. I can have that. That also a spanning tree, yes. Or I can have this. Dun, dun, dun. That's also a spanning tree. But if I go look at the background, said this is 7, this is 5, this is 3, this is 7, this is 5, this is 2, this is 7, this is 3, this is 4, and that's it. All right, or I can have 1, 2, 3, 4. There you go. I can have 7, 3, and then a 1. I can have that. That's also a spanning tree. But you can see here when you add all the weight of all edges, you want to find which one will produce the smallest weight. So the option is, yeah, that is the option. So you look at those connected, you have 1, 2, 3, the total would be 6 compared to every other thing. So this is 15, right? This guy is 14, this guy is 14, and this guy is 11. Versus this one here, 2, 3, and 1, that's only 6. So that's the smallest spanning tree, right? You can see here, we have 5 different possibility of a spanning tree. Yeah, so we have 5 different possibility, but which one give you the smallest spanning tree? So for that, we're gonna take a look at 2 algorithms. So the first one is called Prim algorithms. So how Prim algorithm look like? So same concept with the discard algorithm. So you start with one vertex, you look for all the neighbor of that vertex, and then you only travel to the neighbor with the smallest weight. And then you continue the journey with that new neighbor, and you keep travel to the rest of the vertices with the smallest weight possible. And once you have everything covered, then you have yourself a minimum spanning tree. That's what Prim algorithm is, right? You go one vertex at a time, look for the neighbor of that vertex, and then you try to only go through the one that with the smallest one. Okay, that's the idea to that. So here's the example. So suppose we have this graph. It's not a tree. So we try to build a tree out of this graph that have the smallest weight. So, you know, for convenience, I'm just gonna pick a vertex A, right? So on the exam, I will tell you what designated vertex you should pick, and then you can go from there. But then regardless what, you're just gonna get one small spanning tree with a smaller weight later on. So I'm gonna choose vertex A as the designated vertex. So you can see here, A have 2 neighbor, which is B and D. So if you wanna go from A to B, it takes you 4 steps. You wanna go from A to D, it takes you 1 step. So of course, you're gonna go with the one that's smallest. So you're gonna go A to D will be 1, right? So here we go. So we have A is the neighbor of B and D. So I have 4 and 1. So now 1 is smaller than 4. So I'm going to go with 1 instead. So remember, 4 you don't throw away. You still have there as a possibility. So yeah, so you can have that. So now I look at the neighbor of D. So D have 3 neighbor, which is B, and then H, and then J. So now I have 4, 5, and 6. Therefore, I will pick the smallest one, right? You can see here. Now D have 3 neighbors, 4, 5, 6. So you can see here, out of 4, 5, 6, I always pick the smallest one. But you see that if you go from B, it's take you 4 units. When you go from A, it take you 4 units. But then if you look at the triangle ABD, it will create a circus. So that's no good. So we need to throw one of those away. So you know we can have that. But definitely we have to travel to B no matter what, because 5 and 6 is bigger than 4. So I pick one of those. So yeah, let's say we travel that. We're gonna go to B, and then now you need to look for all the neighbor of B. So now the neighbor of B will be J, and then will be C. So now you look at all the weight of that neighbor. So you're gonna go from B to C. That will be 4 extra units. You're gonna go from B to J will be 10 extra units. So now you have 4, 5, 6, and 10 on the table for comparison. Okay, so you can see 4, 5, 6, and 10. 4 will be the smallest way. So the next destination will be C. So again, the one in blue is still out there, so we don't throw that away yet. Okay, so we keep that for comparison. So now next one we go to C. So now C have 2 neighbor, which is E and F. The unit for each will be 1, 2, 4, and that. So here you go. You have 1, 2, 5, 6, and 10. Now all of that you can compare, and the smallest step you can take will be 1. So the next destination will be F out of everything. There you go. So now the next destination is F. So F has 2 neighbor, which is G and I. So now you have 2, 3, 5, 5, 6, and 10 to compare. So the next destination, you have to go back to E, because that's the smallest out of everything. Okay, so there you go. So now you go to E, and then of course you can see here that E have neighbor of G. So now you have things to compare. You have 5, 6, 10, 2, 3, 5. So the next destination will be G for sure. So that will take care of another 2 units. Okay, and you can see that, and you can see that, right? Let me go back to that. Okay, so if you look at the vertices C, E, F, G, right? You look at the vertex right now, C, E, F, G. Okay, so among that vertices, 1 already taken, 2 already taken, and now this guy 2 already taken. So the 3 will create a circus. So we will eliminate that that edge, because it's already created a circus. We don't want that, so we're gonna erase that. Yes. All right, so next destination will be G. So G have neighbor J and I. So now we still have those number up to compare. You can see here 5, 3, 4, 6, 5, and 10. So out of that, the next neighbor will be J, will be I, because that's the smallest of 3. So you're gonna go there. All right, so go back to that one more time. So now we're gonna go to 3. So this one already check up, check up, check up, and then 3 already check up. So 5 will create a circuit. Yes. So 5 will create a circuit. So therefore we need to get rid of that. Make sense? You have that, you will create a circuit. You don't want that, so you get rid of that. And so the next destination I can have will be J. So now you have 3, 4, 10, 6, and 5 up to compare. So now the next decision you want to go is 3. So there you go. You want to check that. So once you check that, this guy you need to eliminate, because you will create a triangle here, GIJ. Yes. So that's when you need to eliminate. All right. And then since you eliminate that, so now we cover pretty much everything. Now you want to go from J to H. So that's the smallest. So you're going to check that. So because that's smallest, you want to get rid of 5, you want to get rid of 6, you want to get rid of everything that we make a circus after you do a comparison of everything. So that's how we create a new graph from the old graph, and it doesn't have any circuits, and that will give you the smallest spanning tree. So that's what we call a minimum spanning tree. Now, does that make sense? Okay, so you want one vertex at a time, and we keep go through that so that we don't create any circuits with the smallest value possible. So that's what we call a minimum spanning tree. Okay, there you go. That's the original graph, and that's the new graph, a minimum spanning tree that we're gonna have. That's good. Okay. All right, so here's the example. Again, you can pick a vertex A to be your designated vertex for convenience, right? So you can see here, you can go there, you can go there, everything's still there, but next vertex should be B, and you can go there, you can go there. So next vertex should be F, and then you don't want to go back because that will create a loop. So you're gonna go here, and you're gonna go there. Okay. So now the J will be much better. So you're gonna go back here, or you're gonna go to that guy, and then you don't want to go back here. That's create a loop. So you want to go extend it. You want to go back there. Also loops. You're gonna go here, and then you can go back there, and then you can you want to go up there, and then you can go back here. And then now you can erase that guy because that's bigger than that. So you can go down here, and you can delete this guy because that will create a loop. And there you go. You get yourself a minimum spanning tree. Okay. So here's one example. Here one possible solution that you can have. Okay. So what I give you is just one possibility, but then there's a lot of possibility out there you can do, right? So this is just one possible answer. And the minimum weight should be 24. Okay, so again, this is not the final answer. There will be other option too, as long as you get the minimum weight will be 24, regardless where you travel. So 24 will be the best we can do on this graph. Okay, so that's Prim algorithm, one at a time. So the next algorithm will make life easier. We call Kruskal algorithms. So what is Kruskal algorithm? How is that different from Prim? So Prim, you go one vertex at a time. So Kruskal, you don't go one vertex at a time. You organize everything in as a segment. So you're gonna go from smallest to largest with alphabet order with the weight also, and then you go back and connect two pieces at a time, right? So that you can have the option. So you don't start with any vertex. You kind of cut all the vertices out, right? And you lay them out on the floor, and then say, okay, which one have the smallest weight? I'm gonna go with that one first, right? That's the difference between Kruskal and Prim. Prim, you pick a vertex, you go from one at a time. Kruskal, you lay out everything from order, from largest to smallest, smallest to largest, and you start from there. All right. So here is the complete graph. So I'm gonna cut all the edges out. So you can see here, yes? AB will be 4, and then AD will be 1, and then BC will be 4, and then BD will be 4, and then BJ will be 10. So I cut out every single edges. So you can see the old graph to the new graph, we cut them out. And then we're gonna rearrange them from ascending orders, okay? So we're gonna rearrange them from ascending orders, and due to comparison, we always use alphabet letter, right? You can see here A to D, the unit of 1, C to F, unit of 1, so they're on the parallel line on the same side. All right, so let me show you this compared to the previous one. Previous one, we just cut everything out, right? And then we arrange them from smallest to largest. And you will connect the one with alphabet order. So for example, you can see CE and EG are both unit of 2, and HJ also both unit of 2. But if we have a choice, we would go with CE and EG first because those are the smaller alphabet order compared to H to J, okay? So that's the idea. And then, when you connecting one at a time until you cannot go any further, and that will give you a complete, minimum span and tree. So let's go. All right. So we're going to go connect AD. We're going to connect AD. Okay. So that's done. And the next one on the list will be CF. All right. Because those are both unit of 1. So the next one will be CE. The next one will be EG, because they're both unit of 2. And the next one will be HJ. That's also unit of 2. So that's how Crucial work compared to Prim, right? So there we go. And next one will be FG. That's the next on the line. So FG. But what happens? When you connect FG, you will create a circus. Yes, you can see here. When you connect FG, you create circuit. So that's a bad one. So we're gonna throw that away. Okay. So therefore, the next one on the list, if we cannot connect to FG, will be GI. Yes. So go with GI. There you go. GI is good. We don't have any circuits. So next one on the list will be IJ. So IJ, that's also good because we don't have any circuits. So all the 3 units are done. Now moving on to the 4 units, you can go with AB because AB is before BD. So with alphabet order, we go with that. And then next one will be BD. But again, what happens? You will create a circuit. So BD is bad. You're gonna throw that away. So next one will be BC. Since we throw away BD. And next one is GJ. Where's GJ? All right, where's GJ? Okay. So and you can see here, GJ will create a loop again. So you can see that we connect every single vertex already with the smallest path possible. And there we go. We don't need the rest because we already have all the vertices connected with the smallest weight on each edge. So that's what Kruskal algorithm is. Okay. So Kruskal algorithm would be much easier than Prim algorithm, but we have to lay them out in order first before you can go and connect the graph one at a time, right? So Kruskal would be a better graph. So there you go. So you can see that Kruskal and Prim, they both give you the same graph no matter what, but Kruskal algorithm will be much faster than Prim algorithms, okay? So here is the example we can try out for Kruskal algorithm. So let's list them out in order first. So yeah, so you can see unit 1 we have BF. Okay, so we have BF. And then next one is CD. So next one will be KL. So unit 2 will be AB. And next one on the list will be CG. All right, so that's alphabet orders. The next one on the list with the unit of 2 would be FJ. All right, alphabet orders. The next one on the list would be AE. The next one would be BC. And next one with the 3 will be FJ. And the next 3 will FG. Yes, FG. And next one on the list will be GH. Next one on the list will be HL. And next one on the list will be IJ. Next one on the list will be JK. So that's all the magnitude of 3. Next one on the list will be EF, unit of 4. And then EI, unit of 4. And then next one is GK, also 4. And then last one is DH, that's the 5. And there we go. Now we go back and see we can fill it up. So BF, good. So check mark. And CD, check mark. KL, check mark. AB, check mark. CG, again, try not to create any loops. So CG, check mark. And then FJ, check mark. AE, check mark. BC, yep, BC should be good. There's no loop, so check mark. And then FG, is FG any good? So no, FG will create a loop, so no good. And then GH, GH should be good. It doesn't create any loops. And then HL also good. It doesn't create any circuit. IJ should be good. It doesn't create any circuit. And then JK, JK is no good because it will create a circuit, right? You can see here, it will put JK, we create a circuit, so that's no good. And then, yeah, so you can see here, we already cover every single vertices, and all of the rest, we don't really need those. Done, 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 and done. Okay, so that's crisscross algorithms. Make sense? Yeah, that's crisscross algorithms that we can have. Okay. So that's the end of the lecture for chapter 11. Right, I will see you on the next chapters.